Every religion in human history has tried to answer one question: why is there something rather than nothing? Every civilization that looked at the night sky and felt the weight of its existence asked the same thing, in different languages, through different stories, with different names for whatever they believed was responsible. For most of history, physics had nothing to say about this. Physics described how things moved, how forces acted, how energy transformed from one form to another. It did not address why any of it existed in the first place. The question belonged to philosophy and theology. Then, in the 20th century, physics backed into the question, not by looking for God, not by attempting to prove or disprove any theology, but by following the equations far enough that the equations ran out. What physics found at that edge is stranger, more honest, and more astonishing than either side of the debate usually admits. Physics did not answer the question. It made the question precise. And the precision is itself one of the most remarkable things physics has ever produced. Consider the constants, the fixed numbers embedded in the laws of nature that determine how everything behaves. The speed of light, the gravitational constant, the mass of the electron, the strength of the electromagnetic force, the cosmological constant that governs the expansion rate of space itself. These numbers are not derived from any deeper theory. No equation explains why they have the values they have. They are measured, not calculated. They simply are what they are. And they are set to values so precise that if any one of them differed by a fraction, in many cases a fraction so small it defies ordinary language, the universe would contain nothing. Not nothing interesting, nothing at all. Change the strength of gravity by 1 part in 10 to the 40th power. A 1 followed by 40 zeros, a number so large it has no meaning in ordinary experience. And stars either cannot form or burn so fast they explode before planets can coalesce around them. Change the strong nuclear force by 2%, and hydrogen cannot fuse into helium, which means no stellar energy, no heavier elements, no carbon, no oxygen, no chemistry of any kind. Change the mass ratio between protons and neutrons by a fraction of a percent, and stable atoms cannot exist. The periodic table collapses, and with it every material structure in the universe. Change the electromagnetic force by a few percent, and electrons cannot orbit nuclei in stable configurations. Chemistry becomes impossible. Change the ratio of matter to antimatter in the first fraction of a second after the Big Bang by 1 part in a billion, and the universe contains either no matter at all or so much matter that gravity collapses it back into a singularity before atoms can form. The cosmological constant, the energy density of empty space, which governs whether the universe expands, contracts, or holds steady, is set to a value that Paul Davies described as the most astonishing fact in all of physics, precise to roughly 120 decimal places. If it were larger by 1 part in 10 to the 120th power, the universe would have expanded so fast that no structure could form. No galaxies, no stars, no planets, no atoms, no molecules, nothing but a thin spray of particles racing away from each other forever. If it was smaller by the same fraction, the universe would have collapsed back on itself within moments of the Big Bang, everything crushed back into the singularity before the first proton had time to stabilize. 120 decimal places of precision. To put that in perspective, the most precisely engineered object human beings have ever built. The mirrors in the LIGO gravitational wave detector are polished to a precision of roughly 10 to the minus 19 meters. The cosmological constant's fine-tuning exceeds that by 100 orders of magnitude. No known physical mechanism explains why it has this value. No theory predicts it. No deeper law requires it. The constant simply has the value it has, and that value happens to be the 1, out of an inconceivably vast range of possible values. That permits a universe containing structure, chemistry, and eventually beings who can measure the constant and wonder why it has that value. Roger Penrose calculated the improbability from a different angle. Not the constants themselves, but the initial conditions. The specific arrangement of matter and energy at the Big Bang that would produce a universe with the low entropy required for structure to form had a probability of 1 part in 10 to the 10 to the 123rd power. That number is so large it cannot be written in ordinary notation. It has more zeros than there are particles in the observable universe. Penrose himself said it could not be written out in full even if every particle in the observable universe were used as a digit. The initial state of the universe was not merely unlikely. It was unlikely to a degree that exceeds the capacity of any analogy to convey. And yet the universe began in precisely that state, the one state that produced the ordered, structured, low-entropy cosmos we inhabit. If you have spent a lifetime being told by one side that science disproves the need for God, and by the other that faith requires no engagement with what science has found, the fine-tuning is where neither position is comfortable. The universe is arranged as if calibrated to produce complexity. Stars, planets, chemistry, life, consciousness. The calibration is precise beyond anything human engineering has ever achieved. And no one, not a single physicist, theologian, philosopher, or mathematician, knows why. The observation is solid. The explanation is genuinely open. And the openness is the actual state of the science. Trace the history of the universe backward in time, and physics performs with extraordinary precision. The cosmic microwave background radiation, the afterglow of the Big Bang, detected in 1965 by Arno Penzias and Robert Wilson at Bell Labs, provides a snapshot of the universe at roughly 380,000 years old. Before that, the universe was too hot and too dense for light to travel freely. The equations of general relativity and quantum field theory can push further back. Through nucleosynthesis at 3 minutes, through the quark-gluon plasma at 1 microsecond, through the electroweak unification at 10 to the minus 12 seconds. Equations can reach back to 10 to the minus 43 seconds after the beginning, the Planck time, the smallest meaningful unit of duration in known physics, the point below which the concepts of space and time as physics understands them cease to apply. At the Planck time, the entire observable universe was compressed into a region smaller than an atom, at a temperature exceeding 10 to the 32nd degrees, at a density where gravity and quantum mechanics, the two pillars of modern physics, which have never been successfully unified, collide. And then something happens that physicists do not like to talk about. The equations produce infinities. The mathematics breaks. The tools stop working. What happened at t equals 0, or whether t equals 0 even means anything, whether before has meaning when time itself may have begun at that point, is not a question physics can currently answer. The beginning is precisely where the equations go silent. The moment that feels like it should be the answer, the origin of everything, the first instant, the place where the question of why there is something rather than nothing should find its resolution, is the one place the most powerful investigative tools in human history cannot reach. Every person who has looked at the night sky and wondered where all of it came from is standing at exactly the same edge the equations reach. Physics arrived there with instruments precise enough to measure temperature fluctuations in radiation that has been traveling for 13.8 billion years, and found the same open question waiting that was there before the first telescope was built. The silence at the boundary is not a failure of physics. It is what rigorous investigation looks like at the edge of the knowable. Georges Lemaitre understood this boundary better than almost anyone, because he stood on both sides of it. Lemaitre was a Belgian Catholic priest and a physicist, ordained in 1923, doctorate in physics from MIT in 1927. In that same year, he derived from Einstein's field equations that the universe must be expanding. Einstein himself had added a term to his equations, the cosmological constant, specifically to prevent this conclusion, because the prevailing assumption was that the universe was static and eternal. Lemaitre showed Einstein that his own equations, without the artificial constant, demanded expansion. Einstein reportedly told him, "Your calculations are correct, but your physics is atrocious." Think about that for a moment. The man who wrote the equations telling the man who solved them that he was wrong. 2 years later, Hubble's observations of galactic recession confirmed that Lemaitre had been right. The universe was expanding. Einstein later called his cosmological constant the biggest blunder of his career. Lemaitre worked backward from the expansion to propose that the universe had expanded from an initial state of extreme compression, a single quantum, he called it, the primeval atom. He proposed what we now call the Big Bang. A priest proposed it. The physics demanded it. And the Vatican, which might have been expected to celebrate a creation moment, was cautioned by Lemaitre himself not to interpret the Big Bang as proof of Genesis. He warned Pope Pius XII directly against using the expanding universe as evidence for creation, because Lemaitre understood, with a clarity that many later popularizers lacked, that the physics described the expansion. It could not describe what, if anything, preceded it or caused it. The equations told you how the universe expanded. They could not tell you why the universe was there to expand. Lemaitre stood at the intersection of physics and theology more honestly than almost anyone before or since. A man who believed in God and refused to use physics as proof. A man who did physics and refused to let theology influence his equations. Both disciplines were real to him. Neither could do the other's work. Now, he was right. 80 years of subsequent cosmology have not changed this. The boundary has been refined. The equations have been pushed closer to t equals 0. The Planck time is better understood. But the silence at the boundary remains. Physics arrives at the origin with the most precise instruments human beings have ever built, and finds the same open question waiting that was there before the first equation was written. Silence at the boundary provoked attempts to fill it, and the most ambitious came from Alexander Vilenkin and Stephen Hawking. Vilenkin, in 1982, proposed that a universe could arise spontaneously from a quantum vacuum through a process called quantum tunneling, analogous to the tunneling that allows a particle to pass through an energy barrier it classically could not overcome. In quantum mechanics, there is a non-zero probability that a system confined to one side of an energy barrier will appear on the other side without having crossed the barrier in any classical sense. The particle does not go over the wall. It does not go through the wall. It appears on the other side as if the wall were not there. Vilenkin applied this to cosmology. A universe could tunnel into existence from a state of no classical space-time, from a quantum state in which neither space nor time exists in the form we recognize, but in which the probability of a universe appearing is not zero. If the probability is not zero, quantum mechanics permits it, and given enough. But here the language fails, because given enough time presupposes time, and time is part of what tunnels into existence. You see the problem. Hawking and James Hartle in 1983 proposed a related model, the no-boundary proposal, in which the universe has no initial boundary, no edge, no t equals 0 in the traditional sense. In their formulation, imaginary time, a mathematical technique in which time is treated as a spatial dimension, replaces real time near the origin. The universe in imaginary time has no beginning and no end. It is a closed, self-contained geometry, like the surface of a sphere that has no edge but is finite. The question of what came before loses meaning, because there is no before in the geometry. The universe simply is, a four-dimensional shape without an initial boundary condition. Both models are mathematically coherent. Both generated genuine physics, testable predictions about the geometry and temperature fluctuations of the early universe that could be compared against cosmic microwave background data. Both were presented, particularly in popular accounts, as showing that the universe could arise from nothing, that physics had closed the creation question. David Albert, a philosopher of physics at Columbia University, made the critical objection in a review that was more important than many physics papers published that year. Albert pointed out that the quantum vacuum is not nothing. It is a quantum field, a physical entity with structure, energy, mathematical properties, and specific laws governing its behavior. The critical point, the uncertainty principle that permits virtual particles to flicker in and out of existence, is itself a law of physics. It presupposes physics. Vilenkin's tunneling occurs within a framework of quantum mechanics that already exists. You cannot explain the origin of existence if your starting point already contains physics. And here is the part that matters. Nothing, true nothing, The nothing that the philosophical question is asking about would be the absence of everything. No space, no time, no fields, no laws, no mathematical structure, no quantum mechanics, no uncertainty principle, no framework within which anything could occur. Not empty space, not a vacuum, not a field at rest, the absence of the field. The absence of the space the field would occupy, the absence of the laws that would govern the field's behavior. That is the nothing the question asks about. And neither Vilenkin nor Hawking addressed it, because the tools of physics cannot address a state that contains no physics. The question has been pushed back one level. Not why is there a universe, but why is there a framework? Quantum fields, mathematical laws, the uncertainty principle itself, within which universes can arise. Why is there something, even a quantum vacuum, rather than nothing at all? That question, why is there a framework rather than no framework? Why is there physics rather than no physics? Is the one no tool built from within physics can address. It is the edge. And it is worth sitting with for a moment, because this is the point where the question stops being abstract and becomes personal. You are made of matter that exists within this framework. Your consciousness arises from processes governed by these laws. The question of why there is something rather than nothing is not a question about something distant. It is a question about why you are here, why anything is here. And the honest answer is that no one knows. Stated plainly, the universe from nothing claim is the universe from quantum fields. The question of why quantum fields exist, why there is a physical framework at all, rather than absolute nothing, not even a vacuum, not even laws, remains exactly where it was. The question has been made more precise. That is different from being answered. One more response to the fine-tuning problem emerged from physics, and it is the most controversial. If an enormous or infinite number of universes exist, each with randomly varying physical constants, then fine-tuning stops being mysterious. We could only find ourselves in one of the rare universes where the constants happen to permit the existence of observers, the way a fish could only find itself in one of the rare environments that contains water, even if most of the landscape is dry. The cosmological constant is not calibrated, it is random, and we exist in a universe where the random value, by chance, permits structure, chemistry, and observers who can measure it. This is the multiverse, and it emerges naturally from inflationary cosmology, the theory that the early universe underwent a brief period of exponential expansion that stretched the subatomic region to cosmic scales in a fraction of a second. In many versions of inflationary theory, the process that inflated our observable universe also generated others, potentially an infinite number, each expanding in its own bubble, each with different physics, most of them sterile and empty, a vanishingly small fraction containing the constants that permit complexity. Mathematically, the multiverse is well motivated. It solves the fine-tuning problem elegantly. And it faces one fundamental difficulty: it is untestable. No observation from within our universe can confirm or deny the existence of other universes. No signal can cross from one inflationary bubble to another. The multiverse makes no prediction that could be checked against data from this universe alone. By Karl Popper's criterion, that a scientific theory must be falsifiable, must make predictions that could in principle be shown wrong. The multiverse does not qualify as science in the traditional sense. Whether it constitutes an explanation depends on standards of evidence that physicists themselves disagree about, vigorously, publicly, and without resolution. Perhaps the multiverse is true. It may be the correct explanation for fine-tuning, and it may be permanently beyond the reach of experimental verification. All three of these can be true simultaneously. If you have been told that science has answered the fine-tuning question, the answer is disputed, possibly untestable, and accepted by some physicists partly on aesthetic grounds, because the alternative explanations make them uncomfortable. Discomfort is not evidence. Elegance is not proof. And that distinction matters, because the multiverse sits at the boundary between physics and philosophy, and the boundary is not where most popular accounts place it. What makes the multiverse discussion accurate is acknowledging what it does and does not accomplish. If it is true, It explains why the constants have the values they do. We are in the bubble where randomness produced workable physics. But it does not explain why there is a multiverse. It does not explain why the inflationary process generates bubbles. It does not explain why quantum fields exist, or why mathematics describes them, or why there is something rather than nothing. It pushes the question back. Just as the quantum vacuum pushed the creation question back, the question remains. The framework within which the question is asked has become more sophisticated. That is progress. It is not resolution. Every attempt to answer the question, quantum tunneling, the no-boundary proposal, the multiverse, has produced genuine physics, genuine mathematics, genuine insight. And everyone has pushed the question back rather than closing it. The tools get sharper, the question gets deeper. Beneath all of these questions sits one that may be the deepest physics has ever encountered, and it was articulated not by a cosmologist, but by a physicist of mathematics. In 1960, Eugene Wigner published a paper with a title that has echoed through 6 decades of physics on the unreasonable effectiveness of mathematics in the natural sciences. Wigner's observation was simple and devastating. Mathematics was developed as pure abstract reasoning, the manipulation of symbols according to logical rules, with no reference to physical reality. Mathematicians do not look at the universe and describe what they see. They construct formal systems from axioms and explore their consequences. What makes Wigner's point so sharp is that the systems are invented, the axioms are chosen, the results follow from logic alone. And yet, consistently, repeatedly, across centuries, these abstract constructions turn out to describe physical reality with perfect precision. Maxwell's equations for electromagnetic fields, written in 1865, predicted radio waves before anyone had observed them. Dirac's equation for the electron, written in 1928, predicted the existence of antimatter before it was discovered. But the most striking example spans a century. Albert Einstein published the field equations of general relativity in 1915. The equations predicted gravitational waves, ripples in spacetime produced by accelerating mass. Gravitational waves were detected in 2015, a century later, by the LIGO Observatory, matching Einstein's predictions with extraordinary precision. An equation written before either World War predicted a phenomenon detected by an instrument that would not exist for 100 years. And the prediction was correct to more decimal places than the engineering could measure. Mathematics invented for its own sake, with no physical motivation, describing physical reality before the reality was observed. Wigner called it unreasonable because no explanation exists for why it should work. The universe is not required to obey mathematics. There is no physical law that says physical laws must be expressible in mathematical form. There is no logical necessity that abstract reasoning conducted by primates on a small planet, a species that evolved to find food, avoid predators, and navigate social groups, should correspond to the deep structure of reality at scales from the subatomic to the cosmological. The mathematics that describes quantum mechanics was not developed by observing quantum phenomena. It was developed as abstract algebra, group theory, Hilbert spaces, operator algebra, by mathematicians who had no idea their work would one day describe the behavior of electrons and photons. The mathematics was ready before the physics needed it. As if the universe had been waiting for someone to write down the right symbols. And yet it does. Every law, every force, every particle, every interaction, describable with mathematical precision that has never failed when the mathematics was done correctly. Not approximately, not roughly. With a precision that, in the case of quantum electrodynamics, matches experiment to 12 decimal places, the most precisely confirmed prediction in all of science. I find this the most unsettling open question in all of physics, more unsettling than the origin, more unsettling than the fine-tuning, because it sits beneath both. Why does the universe have the character of something that can be understood through abstract reasoning? Why is there a correspondence between the structure of human mathematics and the structure of physical reality? Why does an equation written on a blackboard in 1915 predict a phenomenon detected by a laser interferometer in 2015? A century of correspondence between abstract symbols and physical events with not a single digit wrong. No answer exists. The question sits at the intersection of physics and the oldest human wondering. The sense that the universe is somehow ordered, somehow coherent, somehow arranged in a way that invites comprehension, and the question has no answer. It is the deepest open question in physics, deeper than the origin of the universe, because it asks not just why there is something rather than nothing, but why the something that exists is comprehensible at all. Every person who has looked at the night sky and felt that the universe makes a kind of sense, that it is not random chaos, but something with structure, with pattern, with a character that invites understanding, is registering the same observation, Wigner formalized. Physics confirms it completely. The universe is ordered. It is mathematical. It is comprehensible to an extraordinary degree. And physics cannot explain why. The tools that reveal the order cannot explain it. The equations that describe reality cannot explain why reality is describable by equations. Nothing in physics proves there is a God. Nothing in physics proves there is not. What it has done, with more precision than any previous human endeavor, is make the question sharp. The ancient question, did someone make all this, becomes, why these constants at these values with this precision? Why mathematics? Why something rather than nothing? Why a universe that can be understood at all? Martin Rees, the astronomer royal, wrote that the preeminent mystery is not how the universe works. Physics has made extraordinary progress on that, but why anything exists at all. The universe, Rees observed, could so easily have been empty, that it is not, that it is ordered, fine-tuned, mathematical, and comprehensible, is what physics has to report. What it means is not a question. Physics has the tools to answer. After 13.8 billion years of a universe existing, and a few thousand years of human beings writing down their wondering about why it exists, the wondering is still open. Every civilization that looked at the night sky asked the same question. Every mythology attempted an answer. Every theology constructed a framework. And then physics arrived with the most precise instruments human beings have ever built, pressed the question harder than it had ever been pressed, and found it still open. Only now sharper, more specific, and more astonishing than any previous formulation. That is either the most unsettling fact in science or the most magnificent one. It is possible that it is both. I do not know whether it even means anything to ask why we are here. I have followed the equations as far as they go and found them silent at the edge. I have looked at the fine-tuning and cannot explain it. I have looked at the effectiveness of mathematics and cannot account for it. I find it more interesting to live not knowing than to have answers that might be wrong. None of it frightens me. The question is real. The precision is extraordinary. The answer is not here yet. It may never be. For someone who has spent a lifetime being handed certainty from one direction or another, told by one side that science has disproved the need for God, told by the other that faith requires no engagement with what science has found, the posture of honest uncertainty may be the most useful offering physics has on this subject. Not because uncertainty is comfortable, it is not, but because it is accurate. The fine-tuning is real and unexplained. The silence at the origin is real and unresolved. The effectiveness of mathematics is real and unreasonable. The question of why there is something rather than nothing remains exactly as open as it was before the first equation was written. Only now it is sharper, more specific, and more astonishing. Standing at the edge without retreating to either side, without the false comfort of premature certainty in either direction, is not easy. But it is where the evidence places you, and the willingness to stand there, with the question open and the wonder intact, may be the most useful thing physics has to offer on the subject of why anything exists at all.